Hello everyone. Welcome to this tutorial session of 9 on the topic of smart grid basic to advanced technologies. This session will be taken up by me, Mohammad Owais Khan, the Prime Minister Research Fellow in the Department of Electrical Engineering. So as you all know, we are and every week we take a tutorial session for a recap of the video lectures which you have gone through in the last week. So now coming here in this tutorial session 9, what we are going here about, we will be discussing various things like, first solar energy. Then after we will go through some of the basics of the wind energy. We have already, taken up these topics in detail in the previous tutorial sessions, and then after that we will go through about electric vehicle charging, and also we will see how the battery management system works in any in any electrical system or any in solar based energies. Then after that we will go through hybrid hybrid microgrid actually. Okay. So and lastly we will take up some of the questions which we generally take up in the last of this tutorial session, so that you can get better understanding of the topic. Now coming towards here is this. So, so we will start it from the solar power. What is a solar power? It is actually what it is. It is actually a conversion of solar energy, or we can say sun's energy, into electrical energy. So, how this conversion takes place is that we place solar panels on the rooftop or anywhere on the ground where the open space is there. And on these rooftops, sorry, on these panels, what happened here is that uh, solar sun's radiation falls down. And due to this radiation, we already talked about the electron gets energized and starts flow if the circuit is completed. So a battery, we can store this energy in the battery. So actually, this solar energy is a DC power, and as we know that in our household or industrial usage, generally the loads are AC. So in order to use this DC power, we have to convert it into AC. For that, we will be using power electronics circuits. So here it is said that a solar inverter, what it does, it converts the DC power from the PV panels to the AC power, and it can operate in either a grid connected mode or an islanded mode. So I have already discussed about what is a what is a grid connected mode. Those we can say microgrids, those microgrids which are connected to grid are known as the grid connected microgrid, and those microgrid which are not connected with any grid, or if somehow they got disconnected from the grid, they work in an islanded mode of operations. Actually, one of the most important things of the solar inverter is that it has the responsibility to inject high quality current and provide the grid support. So how can it provide the grid support? Like for example, there are any, you know, by using, we've already talked about that uh, it can provide grid support like frequency support, voltage support, or any reactive or any power based support. So based on this, the solar inverters, what happen here is that they help in the quality of the current and also help in supporting the grid. Now here is the PV characteristics or IV characteristics of a solar cell. Okay, on the left side you can see here clearly the current is on the y-axis and the voltage is on the x-axis. So what happens here is that at this point, when the voltage is zero, it has highest current, and at this point, which is also a maximum power tracking MPPT point, which also we can say a maximum power point. At this point, the voltage is also increased from here, but there is certain dip in the current. So at this point, we call this VMP and IMP. Why we call IMP? Because we have taken this point from the calculation that maximum power is generated here, and after that, it comes down to the this much point. It is known as open circuit voltage. Okay, so at this point, the current you can see that clearly the current gets decreased down to zero or minimum value, and at that point we know that that voltage will be is a open circuit voltage. Now, if we see from on the right side, what we say here is that it is PV characteristics. What is power versus voltage? Okay, so power versus voltage characteristics is here. So just a second. Okay, so what happens here in this, you can clearly see the variation of the power with the voltage. As voltage goes on increasing, the power also goes on. And after, at the point of maximum power tracking point, which we MPPT, which is maximum power point, at this point, the power, you can clearly see it has the maximum value. And at that point, we have VMP. Then after that, after this point, the power will goes on decreasing if we increase the voltage. So if we our objective here is to in a solar cell is to get the maximum power. So we will operate our cell around this maximum power point. Now coming here, there are various type of inverters has been used for has been used in converting the DC to AC power. As I have said that the solar power generally stores energy in the DC form in the battery. For if we have to use it, for our for our usage, we have to convert it into AC because generally our loads are AC based. So here in the first stage, we can see a single stage solar inverter. So here what we go here what we see you can see here is that on the left hand side this is the PV panel. It is connected to the DC to AC converter, and then the output of this single stage inverter is connected to the AC grid. So in this way, it is converting the DC power of the solar cell to the AC, and it is supplying the energy to the AC grid. Here we can say that there is only one conversion stage. You can see only one type of DC to AC converter is there, and PV panels are directly connected across the DC links. Okay, this is how it has been done here. So in this, the power losses will be less as compared to other, because there is only one AC to DC converters, and the losses will be less. Sorry. Then after that, we have another solar inverter configuration, which is a dual stage. What happens here is this: in the dual stage, PV panels are connected to a DC to AC converter. Then it is also another stage of conversion happens here for it conversion to DC AC, and it is supplied to the grid. Because there is two conversion stages, the conversion losses will be higher. So now coming toward the single stage solar inverter control. So what happens here is that in MPPT, I have already said about that we will operate our solar cell at the maximum power point. Okay, ठीक है. So what we our solar cell will operate at MPPT point. What is an MPPT point? If I draw here for IV characteristic, so it will be like this. This is a MPPT point, and for a PV characteristic, you can see this is a MPPT. This is a maximum power point. Okay, at that point, the power will be maximum. Okay, so at the our solar cell will operate at this point. Now, what happens here is that after the operation, the voltage is generated, which is known as VDC link, and then the controlling action has been done here with the help of a VCD DC link control. Then after that, the current is injected into the power and AC control, and PLL is connected over here. So and IAC is also given here. And this is all inverter control over here. Then after that, here, so this is a stage for a control of a single stage in which only one DC to AC converter has been used. Now, but in the dual stage, what happens here is that the DC to DC stage extract maximum power from the PV panel based on the maximum power transfer theorem. In most of the cases, these DC-DC are generally boost converters. Generally, boost converters are used, and the DC to AC stage, what it does, it regulates the DC link such that the active power is transferred to the grid. Inverter also provide grid support by controlling the reactive power. So this is the control of a dual stage DC uh, inverter control. Okay. So after this, this is about the brief, how the brief working of any solar cell, how it is connected, how it is transferred to the grid, how energy is converted. Because in generally solar cell stores energy in the form of DC, but our loads are in AC. So we have to convert the DC to AC, and it will be helped by using the inverters. Now coming toward the another form of generation, which is very widely used in the coastal areas where the wind is very large, or those places where wind is very large in an abundant amount, which is known as wind power generation. So what happened here is then I have actually talked about in detail in previous slides. I think in the third lecture we I have talked about how the wind power is generated, the formula to that wind power. Okay, I will. I think if you want to recall it, maybe you can go through that lecture. It is directly proportional to V cube like that. So what happens here is that in the first stage, the kinetic energy of the wind is, it interacted with the these wind turbines, which are play which moves like this. Okay, due to the high speed of the wind, or we can say the kinetic energy of the wind, what happens here is that they rotate these, these wind turbines. After the rotation of these wind turbine, they rotate the gearbox. Okay, and uh, and and due to rotation of the gearbox, a generator's prime mover is moved and the energy is generated. This energy is then transferred to the power converter for the conversion. And then it is connected to a transformer because the wind power always gives the power in the form of AC. So, and after the conversion of power into AC, it is fed to the transformer for the voltage up or down based upon the requirement, and then it is fed to the power grid. So we can say here is that this part is the mechanical energy. Okay, because in this the mechanical part is moving, like the wind is interacting with the wind turbine. This is all gearboxes, and this part is the electrical part where the all conversion or any voltage up and down of this transformer, by using transformer we can do. I have talked about in the in the previous lecture that we generally use DFIG based generators for the generation of this power. What is DFIG? Doubly fed induction generators. Okay, they have a prime mover attached to it. I will show it here in detail. So this is the wind turbine, which is interacted by the kinetic energy of the wind. Then the gearbox is there, which provide the P mechanical. Okay, P mechanical. Based on this P mechanical, there will be a rotation. Okay, and it is connected to the this RSC and GSC. Okay, gate sourcing converters. Okay, then they are all connected to the power transformer and a power grid. So this is the schematic diagram which represent how the power flows across the stator and the rotor of a DFIG. Okay, here is a wind control emulator. It has been shown in your lectures. There is a three-phase rectifier up and 415. This is IGBT, which is based on semicron. Semicron make IGBTs, and then wind collectors emulations has been done. So basically, we can say here that I have, the power, wind power, how it's calculated. We can see here formula here. P is equal to P wind, rho A CP lambda beta V cube wind. Yes, I have told you about it is directly proportional to V cube, and also I have told about this is a constant which is based on the scientist which has developed this wind power calculation formula. What is A here? Area, swept area. Means on which area the wind is enforcing. Means wind is colliding. Okay. Based on that, uh, based on the wind velocity and pitch angle, we can calculate the power, and this power is given to a binary. We can say here this. Then after this, a torque reference is generated, a current reference is generated, and a PI is proportional integral controller is being placed. So this is what it is, armature voltage control of any DC motor. This is the schematic of that. So rotor side control also of DFIG is there. Wind velocity is given, MPPT reference is given, reference frequency is given. Based on that, based on DQ or any control, we calculate all these things. Now coming to what the most important thing here is that the hierarchical control in an hybrid AC DC microgrid. Okay, because I have in starting I've told about we will discuss in brief about solar, then wind, then we will discuss about battery management system. After this, I will discuss in detail about battery management system, how the battery management system works. Then we will talk about EV charging, and we will talk about the microgrid just in this slide. So basically, my what is a smart grid? It is, a next generation power system. We have been talking about this for the last 9 weeks. What is a smart grid? This is, we can say, a digitalized grid where two-way, where two-way power flow can happen. Okay, these smart grid encompass the interconnected microgrid, especially at the distribution level. What happens here is that they also integrate microgrids, but generally at the distribution level, because microgrid generally form at the distribution level. Because the reason behind is that if we are going to integrate any renewable energy sources or battery energy source, or any biomass based energy sources, so the power generated from these microgrids can be easily transferred to the consumers. If Because the reason behind is that because generally the power output of these renewable energy sources is very small. Okay, so it cannot travel like long distances transmission like we use it for the conventional way. And we have also discussed that microgrid work in a grid connected or a solar operation mode, particularly the standalone operation. But the thing is that standalone operation is either intentional or forced. Forced, like some sort of fault or any outages happen that we can do. Intentional means intentional happens when there is a there is a grid congestion, or we can say the peak demand is so much we have to disconnect a microgrid area, certain area. So in that way we can say it is intentional. And we already know that the key generations in microgrids are wind, photovoltaic, solar, micro hydro, biomass, geothermal, ocean waste. If the place is at nearby to the ocean. Fuel cell we also use the traditional rotational based technologies such as diesel generators, energy storage. So these are also the key generation technology in any microgrid. So what happens here is that this comprises of a DC and an AC subgrid interconnected by a power electronics interface. Okay. So what happens here is that, as you can see clearly here, this is a hybrid microgrid. Okay. These are the power electronics interface. Okay, this is these are DC load. Okay, and these is a AC microgrid where AC loads are there or there are synchronous generators are there. Okay, these are some batteries also there. So what happens here is that in any microgrid, in any grid, there are, a utility will be there. Then it is connected to AC AC subgrid we can say. Then it is connected to power electronic circuitry. Then it is connected to DC because in order to connect the DC loads or DC microgrid, we have in a grid connected mode, we have to use the power electronic circuitry so that AC to DC conversion can happen. But the DC microgrid can directly connect to the utility. Okay, so this is how you can see this is the schematic of AC DC, or we can say hybrid. Generally, we use hybrid microgrid. Okay, so there are various components of hybrid microgrid. In physically, AC microgrid, DC microgrid, converters will be there, sensors and controllers will be there. And then we require a communication pattern. What we require? We require a communication pattern. Like there are various protocols, Internet of Things. Okay, there are various intelligent electronic devices also there, which is known as IDs. Okay, the communication is very much important. That's why they form a small part of a smart grid. Okay. Now coming towards the type of converter employed for interfacing. So how we can interlink or how we can connect a DC to AC microgrid or any utility. So there are two types of converters. One is interlinking converter, which are generally known as ILC. They work on the principle such that they have to equalize the DC side voltage with an AC side. So the main aim of ILCs is to equalize equalize the voltage on DC side, okay, with AC side. Now another type of converters is also there known as back-to-back converters. Generally, they are known as BT-BC, back-to-back converters, and they employ what they do. They they employ reference setting control. Okay, on both sides, that is PDC and PAC to be exchanged and are set as a reference to enable power flow. So what happens here and then? Let's say this is AC, this is DC microgrid, and the energy movement will be there. So there will be PAC and PDC. Energy to the PDC only happen if PDC is less than PAC. So there will be requirement. So the AC power flow will towards the DC microgrid or vice versa. Now coming towards the structures of the hybrid AC to DC uh, microgrids. So what happens here in this? This is hybrid where distributed generation is there. AC distributed generation is there. For a DC, we will be using solar. For AC, we will be wind, and there is an storage element like any battery or fuel cell is there. So what happens here is that let's say this is an AC bus. So for a DC distributed generation, DC to AC conversion will happen. So in that way, only they can be connected to an AC bus. But for to DC, AC to DC or AC, with this three-stage conversion. will be done so that it can control, it can be connected with an AC word. Why it has been done? Because we have to control the voltage. Okay, for controlling the voltage, this three step of conversion is being done here. Because if we do not match the voltage level, there will be various outages. Now coming to the storage element, it is also convert. It is connected by a bidirectional. So in this is how, and if we have to connect any DC load, then AC to DC conversion will be will be done, and then AC load can directly be connected to that. Now, there is also another structure of a microgrid. Other than this, how we can connect to how we can connect distributed generation, which are AC DC based. So there is an high this type of conversion microgrid is there in which we add a DC bus. We add a DC bus, so the DC sources of generation will be directly connected. Then AC sources of generation will be connected through the AC to DC, and storage element bidirectional. Means that why we are using the bidirectional, either energy can flow to the grid, to the bus, or it can flow from bus to the storage element for storing the energy. This is generally BSS, battery energy storage systems. So what happens here and there? There is another AC bus because the utility or the grid will be connected on the AC bus. So it is directly connected to the AC bus, and AC loads will also connected to these AC bus. But if we have to transfer the energy from the DC to AC, like for example, if we have to transfer the energy from DC to utility like say DC, it is a solar. So because like for example, assume there is excess solar power available, then we can use the interfacing converters. These converters will be used to connect the DC bus and AC bus, and through these converters the power flow will be going on. So this is how, this is another setting, another structure we can say, the we can connect our microgrid which is hybrid DC or AC. This is one such, this is second such structure. But in this structure we use interfacing converters here. Okay. Now coming to that, in this, what are the we can say here, uh, what is the main features? The main challenge is to manage the power flow across all sources distributed through the two types of subgrid, which is certainly tougher than the previous efforts developed only for AC or DC microgrid. Is the features of this type of the structure is that the mode of operation could be grid tied or standalone, and the control techniques are generally droop control, which I have discussed in the previous step. Now coming to this thing, why we are going to need storages? Why storage is used in microgrid? You can see nowadays there are various, various type of companies which work on the side on the in the field of BSS, battery energy storage systems. Okay, the why we are going, have a larger attention toward this is that the due to the intermittent natures of renewable energy sources or other sources, the storage element are critical part to enable the standalone operation of a microgrid. Okay, or to smooth the microgrid power during grid connected operation. Storage elements can be classified into two capacity categories: capacity storage element and excess storage energy storage element. So what does a capacity oriented energy storage does? It does not have a faster response time, but they are used for a long-term energy balancing to buffer out low frequency power oscillation of a DG output, and it also helps in compensating the intermittency of our renewable energy sources in any microgrid like batteries, pumped storage, pumped hydro electric systems, or compressed air energy storage. and hydrogen storage are the types of the capacity energy storage. But in the but what in the But in the excess energy storage, these devices have a faster response time and they are responsible for a short time disturbance in any microgrid. By providing what they provide high frequency component of power. They can also absorb the high power transient which come with a high power density like flywheel, supercapacitors or any superconducting magnetic energy storage. So these are all we can say here. These all are axis oriented storages. So basically, there has been two types of energy storages. One is capacity, other is axis. So capacity, as the name suggests, you can see here that they are used for generally used for long-term energy storage. Means they are the energy is stored in those in the capacity-oriented storages so that they can buffer out any low frequency oscillation and also compensate the intermittency. What does it mean? It means like, for example, uh, if there is requirement of power at any time which are non-solar hours, at those hours the energy cannot be generated from the RE, or it happens that there is any cloud like that, so the renewable energy coming from the uh, solar is not there. So, but let's say there is another case when the energy is high, energy generation is high, but the demand is low. So we can store those energy in the capacity storage. So what happens here is that the energy from these storage can be retrieved back at the time of demand. Okay. Now coming to the management of the microgrid. So the critical aspect of any operation such a hybrid or AC microgrid is the control strategy and the power management scheme, which are essential for providing the operation in both grid connected and a standalone modes. So what happened here is that in microgrid, by considering control tasks and time scale, the management of the microgrid is divided into two parts. One is power management, another is the energy management. Okay, so in the power management here, the objective of the power management is to affect the instantaneous operational condition towards certain parameters such as voltages, current, power, and frequency. The power management strategies also, include voltages, frequency regulation, power regulation, and real time power dispatching among the different sources in the microgrid. But in energy management, the algorithm is matching the total power production to the demand, and it is being done in an optimal way with an emphasis on the desired and the long-term outcome. Factors like fuel cost, capital cost, maintenance cost, mission profiles, and lifetime is being considered in the management of these. Okay. Now there are different power management strategies of the AC coupled. So as I have said, there are two modes of operation. One is grid connected, other is the stand alone. Okay. So, in the grid connected, the power management strategies involves around how much output power is dispatched, and then how much DG and super energy conductors are dispatched power. It is being done through the power balancing mode. Okay. Then another is there how much undispatched power is there. So it is being done through MPPT control or SC type on the charging mode. Then comes the standalone based. power management strategy in which the DC AC bus voltage frequency control, demand sharing by group method, master slave method, or power balancing using model predictive methods. Okay, this is for the AC coupled hybrid network. Now for the DC, there are based on the as you know that when there is a DC bus is there in those structure of the microgrid, which that microgrid hybrid is called the DC coupled hybrid microgrid. In the grid connected, it is being done on the basis of ISC interlinking feature converters. How much is there? Then standalone is being done based on the DC bus voltage control, AC bus voltage control, ISC AC bus control, and then the DG voltage bus control, like Droop methods or any other method. Now, for the power management for AC/DC, it is like this. Now, the classification according to the types of control for energy management in an AC/DC grid microgrid. So there are centralized communication network. This is decentralized. In a decentralized, the physical connections is being done. In a centralized, the communication network uh, will control the energy management. And a distributed means the control will be centralized, but there is also a power management inside these microgrid. So we will. This is the classification regarding centralized and decentralized or distributed communication energy management system. So what happens here in centralized, a communication network is needed. There will be a central node which is the operator, and it will have the access to all these global variables, and the problem of a single point of failure, and if there is the reliability is not very much high. Okay, but in decentralized, the communication network is not needed, but the controls here will be through local variables, and global variables are inaccessible. But in the distributed control, what happens here is that communication is needed, and the peer-to-peer communication is used, but it has a lesser communication channel than a centralized, and there is not a single point of failure. And also, this distributed control strategy access to the global variables. Okay. So now coming towards the droop control. Okay. So what is the droop control law? So in this figure, first it shows the relationship between P and V. P is here and V is here, and this is the DC side. This is the this is the DC side, and this is AC side, and these are the interlinking converters. So what the aim of here the interlinking converter is to equalize the V and F in per unit. This is the relation. So based on that, we can see here droop control. This is the steady point which will link at this point, which will link the voltage and the F in this droop control. Okay. Now this is the hierarchical control architecture in a centralized manner. Like this is an AC load. These are batteries. This is solar power. This is DC generation, this is AC generation, wind turbine, then comes the diesel generator, it is connected to the DC bus. These are connected through inverters. Then after that, this is the AC bus. Then after this is the DC bus. So what happens here? These are all DC loads. Battery is there. Then solar PV is connected directly at various points. Then EV charging can also happen at the DC bus for a DC fast charging. Okay. So the hierarchical control is the tertiary control, which is the operator, energy market. There will be power exchange, optimization, unit commitment, optimal mismatch happens on the tertiary layer. Then in the primary layer, the power and P by Q control happening, voltage, current, and frequency control, islanding detection whether the microgrid is an islanding or not, protection happening over there. This is the primary layer is the fastest layer. Secondary layer is slower than seconds to minute. The fastest layer generally comes to microsecond to millisecond, and then slower layer is seconds to minutes. But and the slowest goes for minutes to hours. In what happens in the secondary layer, any outages happen so that after that the restoration happens and then synchronization happen and the power quality, all these things is being done in the centralized way. Okay, this is a schematic of an ILC with the distributed control methods. Okay, now as we know, decentralized method uses local variable for control. However, due to unavailability of the global control, the method may suffer from inaccuracies in accurate power sharing. But in distributed methods, there is communication channels are there. It has the access of the global variable also, and it also offers peer to peer, like this is mg1, this is mg2. So the energy or the energy transferred between these two microgrid can also happen in the distributed technique, but in centralized techniques they overcomes the inaccuracy issue, but at a cost of a higher communication cost. The communication is very much dense, is high in the centralized techniques. That's why it is very much costly, but it also suffers from a single point of failure. If there is any failure in any communication network in any point, so the control will be taken up by the centralized. It will help in restoration. But in distributed, if any outages happen in any microgrid, other things will go on smoothly. These are the other architectures of the microgrid. First one here is a utility grid. It is connected through a point of common coupling, which is open during the microgrid or islanding mode of operation. Interlinking converters is connected with the DC microgrid. Also, there is another DC microgrid. These are other loads. Then this is AC microgrid, which is directly connected, and this is a AC bus. That's why it is directly connected to this. Additional, like say there is additional AC microgrid, then it will be connected like this. Like this is you know already installed microgrid. Then another microgrid is there which is at 60 hertz. So now the frequency matching will be done through the converter DC microgrid. In this there is additional AC microgrid is there. Okay. In this additional DC microgrid. These are all various architectures of the microgrid which can be, which you can see in any practical application. So what we conclude here from that improper power balancing for can be achieved. Enhance voltage quality at the point of coupling and output terminals. Proportional sharing between the microgrids help in better utilization of power electronic devices. Futuristic systems to integrate locally available but diverse in nature distributed generation, and different levels of voltage ranges can allow the integration of the load which are in a diverse rating. Okay, these are various potential research division potential research directions, which is nowadays done. Like there is a research area in which a self-healing power system techniques are, formed as in case of any natural or man-made disaster happen, the grid can self-heal itself, and these are done with the help of the grid forming inverters. There are another which is very highly, uh, a high research area nowadays, which is cyber vulnerability. As we know that our systems is all on grid. Or we can say that our systems are connected to the communication protocol, and they are all based on IP. Okay, the information flows from one microgrid, one area of power generation to another area of power system through the IPs, and you can know you can and it is quite possible that these communication protocol can be compromised. So the cyber vulnerability is also such area where the research is going. So the main aim of is there to reduce the vulnerability of any cyber physical power system. And another research area is the resiliency. Okay, how much our system is resilient to any cyber attack or something like that. Now comes the most important and trending topic nowadays with the EV charging infrastructure. As you know that there are various policies of the government which has been in place to promote EV charging. So what happens here is that because India has also has signed an agreement to reduce its carbon footprint. For reduction the carbon footprint, it has said that it will increase its renewable share of power generation to around 300 gigawatt by 2030. Okay, and it also has made another pledge that the 30% of the transportation vehicles will be EV by 2030. Uh, that policy is known as EV at the rate 30. Means 30% of the vehicles will be electrified by 2030. So, for the electrification of the transportation network, the charging infrastructure plays a very much high role in it. So, what happens here is that to achieve these ambitious targets, our charging infrastructure must be robust, and it has to be dense, means it should be everywhere so that users can can charge their vehicle without any difficulty. So there are two types of chargers, like you can say AC and DC. So AC charging varies from 2 kilowatt to 22 kilowatt, and uh, and the pin there are three types of the pin. They are of charger like this. This is type 1, this is type 2, and this is 3 pin, which generally we use. But in DC, there is a sophisticated charger which is known as CHAdeMO, and the power ranges from 2 kilowatt to 200 kilowatt plus, more than that. So these are well DC fast charger. They can charge the vehicle in 30 minutes. Okay. So another thing here is that there is, which I will see you can see it in this diagram, there are various modes of charging happening. Like first mode of charging is this much, which is connected by a 3-pin AC charger, and the charger is on board, means charger is on the vehicle. Okay, So what happens here is that the we have to just plug in and it will charge the power will be coming AC. Then this onboard charger will convert this AC to DC conversion inside the vehicle, and the battery will get charged. This is the mode one of charging. Okay, mode one of charging is onboard charger. Okay, in the mode two, eh, uh, what has been done in the mode 2 there is a control pilot and it also same as the mode 1 and it also charges in the by in mode 2 using control pilot the charging is being done. Okay, in the mode 3 type of charger which is a which is this the charger pins is like this. It also charges the onboard charger by using onboard charger and battery gets charged. Now, another here is there, which is the DC fast DC charging, which is the mode 4. In this, there is no need of AC to DC conversion. Directly, you can charge the battery, which is also a very fast way. So that's why this is the mode 4 of charging, which is very fast. Now, there are various DC charging plugs available in USA and Japan. Tesla, which is a very much recognized company in the world, it has EV vehicles or autonomous vehicles also, self-driving vehicles it has developed. This company has developed. So they have fabricated their own charger, which is known as a Tesla DC charger. In Europe, the standards are different, so they have developed the different types of number of pins are different. In USA, Japan, there is also another type of charger which is known as CHAdeMO used in China, the charger name is, the charging plugs. We can say these are charging plugs. Okay. There is another type in which we combine both AC and DC charging plug, which you can see here. So now coming to the architecture of AC of an EV charging station. So what happens here in this is an EV which goes to electric vehicle charging station. Okay. And then this is a control management system. Okay, and this is mobile application. What happens here is that it handles all the grid parameters. Okay, whenever you plug into an EVC, so the power will be coming from utility or either from solar because there are generally actually I will okay. The power is coming from utility or from solar, and all the billing information will be done. After you charge, you get your message on the mobile app based on your how much energy you use. Based on that, it will give value on the mobile, and you can pay over here. So basically, what happens here? I will okay. So there are actually what happens here is that when EV there are different types of charging. How we can charge an EV vehicle. One is uncontrolled, other is controlled, and which all we also known as peak valley charging. Okay. Then comes the dynamic charging strategy. Okay. So what happens here is that what in the let me insert another just a second. Okay. So in the uncontrolled, in uncontrolled, what happens here is that whenever a user feels that it has to recharge its vehicle, it just plug in the EVCS, EV charging station, goes and plug it. It does not do not consider the charging rates, grid congestion, anything. Okay, it does not consider that. It just needs its main aim is to charge, and it has no effect but in the charging rate or like this. So these type of charging is very uneconomical. I can say these are very uneconomical because it will lead to higher charging cost and lead to you know mm, we can say here that lead to instability of the grid. Like say if any 1 lakh users are EV users are there, and if all get connected at any time of point of time, so they can lead to the instability of the grid, and there will be many outages. The power will be interrupted. So that's why these uncontrolled mode of charging of EV is not proposed, or we can say uh, promoted. This is not promoted. That's why uh, there is another mode of charging which is controlled charging of EV. So what happens here is that whenever user needs to charge, it will see the ra- time of usage. What is the time of usage? It is a table, or we can say rate of charge at any specified time. Like for example, 9 to 10, the charging rate is this much. 10 to 11, charging rate is this is all AM. 11 to 12, charging rate is different. 12 to 11, 12 to 1 p.m., charging rate is different. These all are established by the grid operators. Why? Because based upon the congestion of the load, they will assign the charging rates. Like if the congestion is less, the charging rate will be less. If the congestion or the demand of the in the network is high, the charging rate will be high. So what happens here is that in the controlled charging, what does EV user? It sees those rates, and it make a decision based on this rate for the charging of the uh, EV. So what happen here is that it will help in reduction of the peak load. Like this is the load demand, this is time. So peak load like this, like for example, this is the load demand curve of any area. So these are the peak times. So for example, just so what happens here is that for example, uh, for example, these are the peak load time. Okay, so from the time of usage, it can see that if I charge the vehicle in these times, the charging cost of my electric vehicle will be high. So what it does here, what the EV user does, he will charge his vehicle in these regions, if possible. So it will plan its own journey like that, the energy that he can charge the vehicle in these regions. So by charging the vehicle in these regions, what happens here is that it will help in reduction of the peak load, because if he charge here, the peak load will increase, but the user is not charging, it is charging here, so the reduction in peak load will be there. The reduction in the charging cost will be there. So in the owning of EV will be beneficial for the EV user. Now the next comes the control. Next comes the dynamic charging. Okay, which is dynamic charging. Now what is this? Why it is different from a control charging? What happens here is that in a dynamic charging, it is done in the network which are integrated with solar or wind renewable energy sources. For example, let's take solar. So what happens here is that I'm drawing a solar output, P output of a solar with that. So this is like this is a general output of any solar power plant. So you can see here from 11 to, let's say, this is 3 p.m. or 2 p.m. Let's say this is 3 p.m. The output of the solar is very much, is high. Okay. So what happens here is that the operator, which is distribution network operator, it will establish the time of charge like that, so that for example कि अगर कोई EV user charges its vehicle in a solar hour, the benefit of the solar integration will be given. Like for example, कि जब सोलर आवर में वो चार्ज करेगा तो एनर्जी विल बी एक्सेस excess of energy will be available, because the energy will be coming from conventional sources, energy will be coming from the distributed energy sources also. So so there will be energy excess. Based on that, the time of usage rate will be lower for the solar hour, because in solar hour the power will also coming from the solar energy. But after the solar hour, time of usage price will get increased. Why? Reason why? Because the solar generation will be will not be that much. After the will be zero, and the energy will be coming from only from conventional or any battery storage uh, sources. So the time of usage will increase. So this is a dynamic price of charge. So what happens here is that based on the energy axis, the distribution network operator will give a dynamic charges. If the energy axis will be high, the charging cost will be lower, and it will all broadcasted to the user on app. So it will see, okay, now the charging cost is low and I have a power demand in my vehicle, I will charge it. So this is how a dynamic charging works. Now come towards the smart charging concept of optimal integration, which just I have told you about. This is time of use pricing without automated control. Basic control pricing is there. Bidirectional control. Bidirectional control, one thing is also there, which I didn't discuss about that, is vehicle to grid, vehicle to home, vehicle to building, and vehicle to load. Okay, like for example, in the evening you have your EV vehicle at a home, okay, and you have access or of energy over there. So what you can see, you can do here, you can transfer that via energy to the grid, also to your home if you have any requirement, also to your buildings, also to the load. That is the same thing actually, V2X. We generally call this technology is V2X. X can be anything. X can be grid, X can be home, X can be building, anything. Okay, this is V2X. This is a Now comes the dynamic prices with the automated control, which I have just discussed about this, how we can control the dynamic pricing. Okay. Now comes the advantage of smart charging. So I have discussed regarding this. So what is the advantage of any smart charge? Just a minute. Okay. So where are we? So हम कहाँ थे? Advantages of smart charging. So what are the advantages? For the distribution networks, इट हेल्प्स इन मोर होस्टिंग कैपेसिटी. क्या होता है कि अगर हम पीक लोड पे चार्जिंग करते हैं तो हम नंबर ऑफ व्हीकल्स जो चार्ज कर पाते हैं दे आर वेरी लो. बट इफ वी यूज द डायनामिक चार्जिंग और स्मार्ट चार्जिंग, नंबर ऑफ ईवीज विच कैन बी चार्ज विल ऑलवेज इंक्रीज. ज्यादा नंबर ऑफ ईवीज को हम चार्ज कर सकते हैं. और अनदर एडवांटेज इज अ फ्यूअर कॉस्ट, मीन्स कि अब कॉस्ट जो है कम हो गई फॉर बोथ यूजर एंड ग्रिड ऑपरेटर. अब वाई ग्रिड ऑपरेटर के लिए कैसे यू कम हो गई है? बिकॉज फॉर अ ग्रिड ऑपरेटर it does not have to install new energy generations. ओके. सो तो इसी वजह से स्मार्ट चार्जिंग एनर्जी करके हम क्या करते हैं कि जो नए जो जनरेशन को हमको इंस्टॉल नहीं करना पड़ता. विद द करंट जनरेशन वी कैन cater to all these energy demands. फॉर द ट्रांसमिशन पैरामीटर्स के लिए क्या रहता है? लिमिटेशन इन सिस्टम पीक लीड, पीक लोड कम होता है. पीक लोड पे अगर हम चार्जिंग नहीं करते हैं और स्मार्ट चार्जिंग लगाते हैं तो इट विल हेल्प इन द रिडक्शन इन द पीक लोड, अवॉइड कंस्ट्रक्शन ऑफ अ जनरेशन कैपेसिटी. दिस इज आई हैव जस्ट डिस्कस्ड. फॉर बिल्डिंग मैनेजर्स क्या रहता है? टाइम ऑफ यूज ऑप्टिमाइज हो जाता है, टाइम ऑफ यूजेज हो जाता है, पीवी बैलेंस हो जाता है कि मतलब अगर एक्सिस पावर आई हुई है पीवी से, वी कैन translate that into the charging energy, or that और डिमांड चार्ज मैनेजमेंट हो जाता है. लोड बैलेंसिंग हो जाती है कि लोड जो है अनबैलेंस नहीं होता है कि डिमांड ज्यादा हो जाए जनरेशन कम हो जाए. फॉर दैट फिर उसके बाद हमको क्या करना पड़ता है? वी हैव टू टेक सम एक्शंस लाइक कहीं का वो पावर आउटेजेस करनी पड़ती हैं और ऑल दोज थिंग्स. तो इट विल हेल्प इन द लोड बैलेंसिंग आल्सो and the reduction of the connection fee, means we same the billings, all those things. Okay, this is how. This is all you can see here. The importance of the charging of the we can see here the smart charging. Okay. So now come another things that there are various, list of EV charging standard. There are various standard to this. For interfacing, the standard is 62196.123. This is for the plug, socket, vehicle, couplers, anything like that. For communication, the standards 15118.123 and ISO 118982. This is for the vehicle to grid data linking layer and physical signaling. For systems, EV conductive charging system, there are various IEC standards. For battery swapping, because there is also a technology where we swap the battery of the vehicle. Okay, this is generally not possible in India for a four wheelers, but for two wheelers this is possible. What they do here is you take a battery and then you discharge to it completely, and after it gets discharged, what happens here is that you go on to any charging station, you put that battery on the charging socket and take any battery from there and install and just put it in your two wheelers. Okay. There is another standard for the conductive charging. This for GBT 202314 for China and information technology for IT equipment safety means those equipment should be safer for the operation. Now coming to the another topic, which is the battery management system. So why it is very much is very important and trending topics nowadays. Why it is so? The reason behind is that during any usage, during any usage of battery, what happens? Current flows. Current flows, then I square R losses happens. These I square R losses will translate into heat produced in the battery. If there is no thermal management, the battery will explode. Okay, and you can see in the recent news there are various two wheelers vehicles who they have getting caught by fire. Why? Because the thermal management by the system on those vehicles are not very much good. That's why they are getting fire. Reason behind this is the reason behind this is that reason behind is that
another topic, another okay. So that's why thermal management or the battery management system is very much necessary. So what does a battery management system does? It does everything to for the safe operation of a battery. It monitors the current, voltages, and temperature of each cell of a battery, because a battery is made up of different cells and they are either connected in series or in parallel, which I will discuss after this. Okay, so temperature of each cell. Then it also estimate the SOC and SOH and SOL using estimation techniques. What is SOC? SOC is state of charge. Okay. What is SOH? State of health. What is SOC? State of life. Okay. A state of charge tells you about how much energy is there for you can use. Okay. But a state of health tells you about the health of the battery, how long it means how it is deteriorating its health over a period of time. And a state of life, based on these two, will tell you how many years this battery will go on. Okay, work like this. Battery management system also does what it does. It also cell and module balancing. Okay, there are two types of balancing method. One is passive and other one is active, in which balancing method. Okay, it also does calculate the energy and power limit of any battery pack of any battery pack using SOC and SOH labels, SOH values. What happens here is that it estimate these values, and based on these values, it shows that it can store energy around 80% or 90% or 70% based on these values. So there is an schematic of this, like this is, you know, this is a battery. Okay, the measurement of current, voltages and temperature. Then another block is there which estimate the SOC. Then what happens is that then SOH is estimated state of health. Then cell balancing or equalization of cell is done. Then after that, energy and power limits are calculated. Okay, this is being done. Now comes towards the, so this is, you know, a single loop. This is a single loop. In every loop it will be done. So I have told you about why we need a BMS. We need a BMS to monitor operating parameters, okay, to monitor for thermal management, for thermal management, okay. It also used to protect cells from damage in any failure cases. It also helps in prolongs the life of battery. It also maintains the battery in a state which it can fulfill its functional requirements. It also, you know, informs the onboard controller to how to utilize the battery pack, like what are the power limits, all those. Okay, so what is it is how it is connected. So this is, you know, these are cell, these are cells. Okay, these all are connected to form a battery. Okay, and this is all connected to a battery management system. This battery management system is connected to a cooling system or a thermal system. Okay, this is this part is connected, and this part and this part is connected to a contactor control, because we have and pack measurement, any measurement about things. Okay, so these all things are there, and this is all is inside like this, and there is a host application control, which we can say onboard control, host application controller, which is connected to this PMS. So this is a, you know, schematic of a battery management system. Now, so there are various functionalities. So functionality of BMS. We can break down it into various categories, like first, sensing and high voltage control. Sensing in high voltage control. So what it does here? It measures the voltages, current, temperature,
Okay. Temperature control and control contactors, ground fault detection. Okay, and thermal management and thermal management. Okay. Then another functionality of BMS is protection against. It also protect against फर्स्ट ओवरचार्ज की जो व्हीकल है ओवरचार्ज ना हो जाए, ओवर डिस्चार्ज नहीं हो जाए, जो मिनिमम एसओसी है वो मेंटेन रहनी चाहिए, जो करंट जिससे चार्ज हो रहा है इट शुड नॉट बी अबव द स्पेसिफिकेशन ओवर करंट, एनी शॉर्ट सर्किट, these all are the functionality of a BMS. And extreme temperature, like if there is somehow the battery goes on to an extreme temperature, there should be cut off from the power. So this is the functionality. Okay, another functionality of a BMS is battery management is the interfacing. Is interface like range estimation karna based on the SOC and SOC value. Also communication is very much important. Also record the data because we have to see that thing on the on app on a digital display in your car, and then report if there is any outages, so it can report that. So if there any corrective action which need to that, that can also be done. Another operation or the work of the BMS is performance management. Is performance management. Here, what is the performance management? कि state of charge को estimate करना, state of charge को estimate करना, power limits हैं उनका computation. What are the power limits computation? Okay, and then equalization of balancing of the cell. Equalize the cell because एक बैटरी पैक डिफरेंट सेल को ऐड होके बनती है और सेल जो है if we fabricate उनके वोल्टेजेस डिफरेंट हो जाते हैं, उनकी कंसंट्रेशन डिफरेंस हो जाती है, तो उसकी वजह से हमको वोल्टेजेस का सेल्स के वोल्टेज को इक्वलाइज करना है. ओके. Another functionality is diagnostic. Diagnostic is any fault detection. Okay, any abuse detection. These all being done by the, okay, this thing. Okay. अब हमको पता है कि जैसे जैसे बैटरी पैक बड़ा होता जाता है, okay, larger the battery pack, larger it will be the cost, higher is the cost. And the thing is that कि हम ये कैसे पता चले, क्या लगाएं कि हमारा जो बैटरी मैनेजमेंट सिस्टम कितना अच्छा होना चाहिए. ठीक है. इट इज ऑलवेज डिसाइडेड बेस्ड ऑन द एप्लीकेशन, बेस्ड ऑन द एप्लीकेशन. ठीक है. अब आप एक वॉच ओन कर रहे हैं, एक वॉच ओन कर रहे हैं. ठीक है. वॉच में क्या लगती है? एक बैटरी लगती है. अब आप उस बैटरी पे आप बीएमएस नहीं लगाएंगे. क्यों? क्योंकि इट इज नॉट अ वेरी क्रिटिकल ऑपरेशन. हमको पता है इसके अंदर बहुत ज्यादा कॉम्प्लेक्स थिंग है नहीं और बहुत ज्यादा क्रिटिकल ऑपरेशन भी नहीं है. अगर खराब हो जाती है तो हम पूरी की पूरी बैटरी बदल देते हैं. इतनी कॉस्टली बैटरी नहीं होती है. तो बैटरी वॉच पे बैटरी मैनेजमेंट सिस्टम नहीं लगता है. हम कहाँ लगाते हैं? ईवी कार्स की बैटरी पे लगाते हैं. वाई? देखो, ईवी कार की बैटरी के अंदर बीएमएस इसलिए लगता है बिकॉज इट इज अ वेरी कॉम्प्लेक्स आर्किटेक्चर. वहां पे हमें रेंज एस्टिमेट करते रहना चाहिए होता है और वहां पे थर्मल मैनेजमेंट करना. अगर थर्मल मैनेजमेंट नहीं करेंगे तो द पीपल हु आर सिटिंग इनसाइड द कार विल गेट, हैव अ दे मे गेट बर्न और, ओके. तो वहां पे क्या है, ऑपरेशन क्या है? क्रिटिकल ऑपरेशन है. एक क्रिटिकल वे में बैटरी यूज हो रही है, तो इसी वजह से डिपेंडिंग ऑन दैट वी आर गोइंग टू एस्टिमेट कि हम कहाँ पे बैटरी मैनेजमेंट सिस्टम लगाएंगे, कहाँ पे नहीं लगाएंगे. ओके. बेस्ड ऑन दिस, लाइक इसी तरीके से हम ये वो मतलब ठीक है, इसी तरीके से हम एस्टिमेट करेंगे कि बैटरी मैनेजमेंट सिस्टम क्योंकि कॉस्टली थिंग है. व्हाई? बिकॉज यू कैन सी क्लियरली हेयर कि बैटरी मैनेजमेंट सिस्टम में क्या क्या चीजें होती हैं. देखो, इतनी सारी चीजें लगती हैं. वो जो है एसओसी भी एस्टिमेट करेगा. इट विल आल्सो एस्टिमेट एवरी ऑल दोज थिंग्स. ओके. तो इट इज अ वेरी कॉस्टली एप्लीकेशन. ओके. नाउ अब क्या होता है कि एनर्जी ऑफ अ पैक कैसे डिफाइन करी जाएगी? एनर्जी ऑफ अ बैटरी पैक कैसे हम पता चलेंगे कि एक बैटरी पैक में कितनी एनर्जी? उसका एक एक्सप्रेशन है, ई पैक इज इक्वल टू एनएस इंटू एनपी इंटू क्यू सेल इंटू वी सेल. ये बताता है, क्या बताएगा? एनर्जी ऑफ द बैटरी. ओके. एनर्जी ऑफ बैटरी कैसे बताएगा? एनएस क्या है? एनएस है नंबर ऑफ सेल्स इन सीरीज. एनएस क्या है? नंबर ऑफ सेल्स इन पैरेलल. ओके. क्यू सेल क्या है? एक सेल का कैपेसिटी, कैपेसिटी ऑफ अ सेल. अब क्योंकि आइडेंटिकल सेल माने जाते हैं तो सारे सेल की कैपेसिटी एक जैसी ही होगी. एंड वी सेल क्या है? voltage of a cell, which is the cell, voltage of a cell. अब मैंने ये बताया था कि नंबर ऑफ सेल्स इन द सीरीज. अब क्या होता है, जो बैटरी पैक में, एक बैटरी पैक में जो सेल्स लगे होते हैं, दे आर कनेक्टेड आइदर इन सीरीज, आइदर इन पैरेलल और इन बोथ. तो जनरली प्रैक्टिकल यूसेज में सेल इस तरीके से लगे आते हैं. लेट्स से दिस इज C1, this is C2, this is C3, this is C4, this is C5, this is C6. इस तरीके से यहाँ तक ये लग गए सब Cn, Ns तक. अब यही लाइन, यही पूरी लाइन रिपीट हो सकती है लाइक दिस, C1, C2, C3, CNS. और ये कहाँ तक रिपीट हो जाएगी, CNP तक. ओके. तो इस तरीके से हम देखेंगे, ये 1 है, ये 2 है, ये क्या हो गया, NP. तो नंबर ऑफ सेल्स इन पैरेलल कितने आ जाएंगे वो हम लगा लेंगे. तो सभी कैसे कनेक्टेड होते हैं, आपस में तो कनेक्टेड है ही, और ये इधर ऐसे करके कनेक्टेड है, एंड दिस ऑल गिव अ वन पैक. ओके. This is, we can say here is that these are in cell in series, also in a also in a parallel. Based on that, पावर कैसे निकाली जाएगी, पावर ऑफ पैक कैसे निकलेगा, पावर ऑफ पैक कैसे निकलेगा. आई क्या होता है, आई होता है dq/dt. ठीक है. पावर भी कैसे होती है, dE/dt. तो हम NS, NP और V सेल, ये तो कांस्टेंट है, तो dq/dt कर देंगे. तो क्या आ जाएगा, NS, NP, V सेल और I सेल. इस सेल का कैपेसिटी उसको रेट ऑफ टाइम करेंगे तो हमें I सेल मिल जाएगा. तो इससे क्या निकलेगा, हमारा पावर ऑफ द पैक निकल आएगा. ठीक. ओके. तो दिस इज द थिंग. अब इसमें क्या होता है कि हम जो है बैटरी मैनेजमेंट सिस्टम में हम क्या करते हैं, बैटरी पैक का वोल्टेज सेंसिंग करते हैं. तो वोल्टेज सेंसिंग कैसे करते हैं ये हम देखते हैं. हाउ वी आर गोइंग टू सेंस द वोल्टेज. अब now all the voltages, we know that voltage measurement is generally done using the analog to digital converters. ओके. जिसको हम कहते हैं A to ADC. ओके. और there are various several converters ADC, like first is direct conversion, which is also known as flash ADC. It uses a comparator and a fixed reference. Yes. Just a second. Okay. I think actually it got stopped. Okay. This is comparator. Okay, comparator. Next is the successive, SAR. Okay, SAR. It compares the input to output from DAC and uses the feedback. Okay. Another comparator is that a delta, and another architecture of ADC is delta sigma, delta sigma based. Okay. Now coming to the resolution. How we can calculate the resolution of any ADC. तो ADC का resolution क्या होता है, smallest change in the input signal that can be measured. Okay, so let's say any ADC has a m bit output, so it will have 2m output codes. Okay, and for any ADC, so for example, let's say I will take an example to so that you can understand. The input range कितनी है एक ADC की 0 से 5 वोल्ट है ठीक है it has 16 bit of precision तो रेजोल्यूशन Q क्या होगा ये होगा हाई माइनस लो which is 0 divided by how much 2 raised to the power 16 so it will be calculated it will come out to be 76 microvolt okay this is the resolution of any ADC now the thing here is that we will see अब क्या होता है कि मैंने क्या कहा था थर्मल मैनेजमेंट बीएमएस में क्या रहता है थर्मोकपल इसका काम क्या है थर्मो बीएमएस का इट आल्सो यू नो सेंसेस द टेम्परेचर बीएमएस का काम क्या है इट आल्सो मॉनिटर्स द टेम्परेचर तो यहाँ पे टेम्परेचर का क्या यूज किया जाता है थर्मोकपल थर्माइस्टर्स यूज करे जा सकते हैं ठीक है वी कैन ऑल्सो यूज द थर्म अब क्या होता है इसमें कि थर्मोकपल इट इज कंप्राइज ऑफ अ डिसिमिलर टू डिसिमिलर metals okay here in thermistor we use is there are two types of thermistor which is PTC and NTC what is NTC and a negative temperature coefficient and also the PTC is positive temperature coefficient okay so ये क्या measure करता है it measures the resistance based on the resistance it calculate the temperature अब resistance measure करने के लिए हमको क्या चाहिए होता है voltage divider circuit चाहिए होता है voltage divider circuit ओके तो वोल्टेज डिवाइडर सर्किट से हम क्या मेजर कर लेते हैं वी कैलकुलेट द रेजिस्टेंस बेस्ड ऑन दैट इट कैलकुलेट दिस द टेम्परेचर सो बीएमएस का कहने का मतलब ये है कि बीएमएस क्या करता है इट ऑल क्या करता है इट सेंस द हाई वोल्टेज it also protection against the current it also interfaces this all also diagnostic so all these things are done by the uh, BMS okay so now coming towards another thing here which is the sensing of the current अब क्या मैंने क्या बताया था कि बीएमएस क्या ऑल्सो सेंस करता है इट ऑल्सो सेंसेस करंट ओके अब मॉनिटर करंट इलेक्ट्रिकल बैटरी पैक आर रिक्वायर्ड क्यों क्यों रिक्वायर करा जाता है करंट टू मॉनिटर द बैटरी पैक सेफ्टी to report or record any conditions abusive conditions और एसओएच और एसओसी एस्टिमेशन के लिए यूज करा जाता है ओके तो अब इसमें क्या होता है एसओएच एसओसी कंडीशंस के लिए क्यों क्यों यूज करा जाता है वो आई विल एक्सप्लेन इट आफ्टर दिस अब फॉर वी कैन नॉट कैलकुलेट मेजर करंट डायरेक्टली okay so there are two types of method one is a resistive shunt लगा के मेथड resistive shunt method होता है another होता है hall effect mechanism okay hall effect mechanism तो इसमें क्या होता है शंट रेजिस्टेंस शंट में क्या होता है एक रेजिस्टेंस शंट लिया जाता है ठीक है जिसकी वैल्यू अराउंड विच इज वेरी स्मॉल विच इज अराउंड 0.1 million. It is a high precision resistance in series and it is connected in series with a battery pack which is usually at a low voltage. तो फिर I कैसे कैलकुलेट कर दिया जाता है V शंट डिवाइडेड बाई R शंट इस तरीके से देखो मैं इसको दिखाऊं एक ये पैक है ओके ये कनेक्टेड इस तरीके से जस्ट और यहाँ पे एक शंट लगा दिया गया ठीक, बी शंट। तो इस तरीके से हम क्या कैलकुलेट कर लेते हैं, आई। सिंस द शंट रेजिस्टेंस मस्ट बी स्मॉल, स्मॉल इसलिए रखा गया है ताकि इसमें लॉसेस ज्यादा ना हो, क्योंकि हम सीरीज में लगा रहे हैं। ठीक है, वोल्टेज ड्रॉप भी ज्यादा ना हो। एंड देन आफ्टर दैट one terminal is connected to the negative and other terminal of the battery is connected to the output. आप देख सकते हो कि इसमें जो है एक प्लस में कनेक्टेड है, एक माइनस में, और यहाँ पे ये बीएमएस पे कनेक्टेड है। और इसमें से जो वोल्टेज निकल के आया है उसको हमने एम्पलीफाई करा है। क्यों? वोल्टेज ड्रॉप स्मॉल होगा क्योंकि आर स्मॉल है। जब आर स्मॉल है उसको एम्पलीफाई करेंगे ताकि बीएमएस उसको मेजर कर सके। तो रेजिस्टेंस बिटवीन दैट, इस तरीके से हम क्या करते हैं, करंट मेजर करते हैं। देयर आर ऑल्सो अ कनेक्शन विच इज नोन एज कैल्विन फोर वायर कनेक्शन, फोर वायर कनेक्शन। ओके, अब कैल्विन फोर वायर कनेक्शन क्या करता है, इट इट इज वेरी हाई प्रिसीजन मेथड फॉर सेंसिंग द करंट। अब इसमें एक और मेथड मैंने बताया विच इज अ हॉल इफेक्ट, विच इज अ हॉल इफेक्ट। जस्ट अ सेकेंड। ओके, तो हॉल इफेक्ट क्या है? व्हाट इज द हॉल इफेक्ट? एक्चुअली हॉल इफेक्ट क्या है कि इसमें एक कॉइल वॉर्प करी जाती, a coil is wrapped around a primary current carrying conductor. The electromagnetic field produced by the conductor by the conductor induces a secondary current, secondary current in the coil. Okay, तो हॉल इफेक्ट सेंसर क्या करता है, इट measures this induced current to infer the प्राइमरी करंट, जिससे प्राइमरी करंट का पता लगाया जा सके। ओके, अब इसको कनेक्ट कैसे करा जाता है? इट इज कनेक्टेड लाइक दिस। ये है एक बैटरी पैक। ओके, इसको प्लस टर्मिनल से कनेक्ट कर दिया, माइनस से। तो यहाँ पे क्या करा हमने, एक जस्ट सेकंड, यहाँ पे क्या करा हमने, एक कॉइल लगाई। ठीक है, और उसकी कंडीशनिंग करने के बाद उस यहाँ से जो आउटपुट निकाला, तो करंट मेजर करा, उसको हमने एक कंडीशनिंग सर्किट में भेजा। एंड देन दिस गोज टू द बीएमएस, क्योंकि आफ्टर एंड ऑल बीएमएस को ही सब मेजर करना है। ठीक है, तो दिस इज हाउ इट इज कनेक्टेड। ओके। अब इसमें वन थिंग इज देयर वन थिंग इज देयर दैट हॉल इफेक्ट सेंसर्स आर, ये सेंसर्स क्या होते हैं, आर इलेक्ट्रिकली इलेक्ट्रिकली आइसोलेटेड, इलेक्ट्रिकली आइसोलेटेड फ्रॉम द पैक। तो इसीलिए कोई सर्किटरी की जरूरत नहीं रहती, ठीक है। ओके। अब इसमें क्या होता है, देयर इज ऑल्सो ड्रॉबैक, दे सफर फ्रॉम अ ऑफसेट जीरो। ओके, ऑफसेट एट जीरो, which is not our area of interest. This is just like how, what are the drawback to this. तो इस तरीके से हम करंट मेजर करते हैं। अब मैंने बताया था कि करंट मेजर करके हम वोल्टेज मेजर करके एसओएच एसओसी मेजर करते हैं। कैसे? करंट से वोल्टेजेस एंड टेम्परेचर। क्या होता है एसओ एसओसी मेजर करने के, देयर आर वेरियस एल्गोरिथम्स। जनरली आजकल artificial intelligence based algorithm also there, which by using एक algorithm है long short term memory, LSTM, long short term memory. It is a recursive neural network based method. तो इसमें क्या होता है, it requires a large data set, large डेटा सेट चाहिए होता है। वो डेटा सेट किसका होता है, आई का होता है, बी टेम्परेचर, ये एक तरीके का डेटा सेट होता है। एट ईच टेम्परेचर और ईच टेम्परेचर द वैल्यूज आर देयर, बेस्ड ऑन दैट डेटा सेट इट जनरेट्स एक क्या करने होते हैं हमें, आर्टिफिशियल न्यूरल, मैं कहूँगा न्यूरल मॉडल्स बनाने होते हैं, न्यूरल नेटवर्क बेस्ड मॉडल्स बनाने होते हैं। फिर वो न्यूरल नेटवर्क बेस्ड मॉडल एस्टिमेशन क्या करते हैं बेस्ड ऑन दिस, क्योंकि एसओसी क्या है, आई और वी और टी पर डिपेंडेंट है, ठीक है, इन पर ही डिपेंडेंट रहती है। बेस्ड ऑन दैट एसओसी एसओएच ऑल दीज आर कैलकुलेटेड। ओके, दिस इज हाउ a battery management system is done. So now moving on towards the questions, because it's time to end the lecture, then I will solve some questions over here टू अब ये क्या है, एक थोड़ा थ्योरेटिकल टॉपिक है, इसमें क्वेश्चंस काफी कम ही रहते हैं, ठीक। और इसमें मतलब बहुत ज्यादा कोई एज सच कोई क्वेश्चंस बन नहीं पाते। मैं कुछ कोशिश करूंगा, अपने तरफ से लगाऊंगा कुछ क्वेश्चंस एंड देन वी विल सॉल्व। ओके, तो फर्स्ट क्वेश्चन इज, आई थिंक सबको स्क्रीन दिख रही होगी, इट इज visible because sometimes due to internet connectivity it get off. Okay, so I think everyone can see. When will be the exam to be conducted on third? What will be the exam pattern? I think you should have, तुमको पता होना चाहिए ना, पता नहीं होगा कि वो क्या एग्जाम हो पैटर्न है। आई थिंक गो, आप जो है अपनी स्मार्ट, ये जो एनपीटीएल की वेबसाइट है जिस पे जाना, और उस पे लिखा हुआ है क्या स्मार्ट पैटर्न, क्या एग्जाम पैटर्न होने वाला है, ठीक है ना, दैट इज क्लियरली मेंशन्ड। इफ नॉट देन आई विल see it in the next week. Which one is correct in, okay, which one is correct in MPPT mode of solar cell? Solar cell, कौन सा ऑप्शन इज करेक्ट? तो एक ऑप्शन है VOC is greater than VMP and IMP is greater than IS. IMP क्या है? Point at the maximum MPPT for mode. Okay. VOC, open circuit. VOC is less than VMP and IMP is less than IS. C option है VOC greater than VMP, then IMP less than IS. D option है VOC is less than VMP and IMP is greater than IS. ओके, तो इसमें से करेक्ट आंसर बताइए क्या होगा। ठीक है, ओके, चलो देखते हैं क्या है। देखो, शुरुआत में मैंने एक ग्राफ बनाया था विच आई थिंक यू विल सी हियर। देखो, ये ग्राफ है, ठीक है। इसमें यहाँ पे मैक्सिमम पावर पॉइंट ट्रैकिंग हो रही है, ठीक। तो वीएमपी क्या है, ये वीओसी ये है। तो हम क्या कह सकते हैं कि वीओसी ज्यादा है, ठीक है ना। वीओसी ज्यादा है वीएमपी से, एक तो ये बात हो गई। अब आईएमपी का है, आईएमपी ये वाला पॉइंट है, ठीक। और आईएससी क्या है, ये वाला पॉइंट है, ये शॉर्ट सर्किट। तो आईएमपी नीचे की तरफ है, आईएससी ऊपर है। तो क्या कहेंगे हम, आईएससी इज ग्रेटर देन आईएमपी। बेस्ड ऑन दिस हम ऑप्शन देखते हैं कौन सा सही ऑप्शन है हमारे पास। क्या हमने निकाला, वीओसी ग्रेटर देन वीएमपी। तो एक ऑप्शन तो ये है, वीओसी ग्रेटर देन वीएमपी, बट हेयर आईएमपी इज ग्रेटर देन आईएससी, विच इज रॉन्ग। सेकेंड भी रॉन्ग ही। सी देखते हैं, वीओसी इज ग्रेटर देन वीएमपी बट आईएमपी इज लेस देन आईएससी, दिस इज द करेक्ट। ओके, दिस इज। सो नेक्स्ट क्वेश्चन हियर इज, what is the purpose of PLL in solar inverter control। ठीक है, तो ए ऑप्शन है ट्रैकिंग ग्रिड कंट्रोल, ट्रैकिंग ग्रिड वोल्टेज एंड फेज एंगल, ठीक। देन बी है ट्रैकिंग ग्रिड वोल्टेज मैग्नीट्यूड, सी है ट्रैकिंग ग्रिड फ्रीक्वेंसी। ओके, डी बोथ, बी एंड सी। तो करेक्ट ऑप्शन बताओ, क्वेश्चन नंबर 2। सो पीएलएल क्या है, फेज्ड लॉग्ड लूप। इसका काम क्या होता है, वोल्टेज और फेज एंगल को ट्रैक करना। सिंपल है, कोई इसके अंदर ऑप्शन है ही नहीं, ठीक है। वोल्टेज एंड मैग्नीट्यूड एंड फेज एंगल को ट्रैक करना। तो फर्स्ट इज द करेक्ट आंसर। क्वेश्चन नंबर 3, व्हाट इज डीएफआईजी इज टाइप ऑफ मशीन। ए स्क्विरल केज इंडक्शन, बी स्लिप रिंग इंडक्शन, सी both, and D none. तो इसका आंसर बताइए। क्या है आंसर? बी। बी, slip ring induction is the right answer. This is the correct answer. Now, next question here is question number 4. Which is most economical and efficient configuration of microgrid? A. DC coupled hybrid microgrid. B. AC coupled hybrid microgrid. C. AC DC coupled hybrid microgrid. D. Both A and C. तो इसमें बताना है कि कौन सी कॉन्फ़िगरेशन ऑफ माइक्रोग्रिड इज इकोनॉमिकल एज वेल एज एफिशिएंट फॉर अ ग्रिड कनेक्टेड मोड। ठीक है, ग्रिड कनेक्टेड मोड, ये देख लेना, ग्रिड कनेक्टेड मोड। ठीक है, फॉर अ कंटिन्यूअस ग्रिड कनेक्टेड। ठीक है, ये चीज और है। अगर हम कंटिन्यूअस ग्रिड कनेक्टेड मोड ऑफ ऑपरेशन लेंगे तो कौन सा आंसर हमारा सही रहेगा? ओके, देखो क्या है, कंटिन्यूअस ग्रिड कनेक्टेड मोड में क्या होगा कि हमारा जो माइक्रो ग्रिड है, इट इज ऑलवेज कनेक्टेड टू द ग्रिड। तो एसी बस तो होगा। ठीक है, तो हम जनरली पावर जो है वहीं से आएगी, तो उसमें क्या होता है, एसी कपल्ड वाला ज्यादा बेहतर होता है। एसी कपल्ड हाइब्रिड माइक्रो ग्रिड इज द मोस्ट इकोनॉमिकल एंड एफिशिएंट। क्वेश्चन नंबर 5। बीएमएस does which of the following operation? A. Monitor cell voltage. B. Monitor current and voltages and power. Okay. C. Okay. And power हो गया. Then both A and B. B only. So just a second. Not B. Only A. So give me the correct answer. BMS क्या करता है? Monitor cell voltage, monitor current and voltage and power and temperature. Okay, monitor current, voltage and temperature. ठीक, then both A and B, ये दोनों को करता है या only A? So give me the correct answer. C. Okay. So anyone else? देखो क्या है, बीएमएस क्या करता है? बीएमएस क्या करता है, सेल के वोल्टेज को मॉनिटर नहीं करता। ठीक है, ये बैटरी पैक के वोल्टेज को मॉनिटर करता है। ठीक है, ये करेक्ट नहीं, मॉनिटर करंट एंड वोल्टेज इज, तो बी आंसर इज द करेक्ट। ये तो हर गलती हो जा रहे हैं। ठीक। क्वेश्चन नंबर 6, विच टाइप ऑफ चार्जिंग is economical for both user and grid. Okay, which type of charging is economical? Okay, first is uncontrolled control mode of charge, B uncontrolled mode of charging, and C dynamic or smart charge, dynamic charging, and D both A and C. So write the correct answer. I think it is visible. Yes, it is. So here in this, the economical mode of charging is control mode भी charging economical है for both user and grid and dynamic. तो इसीलिए the correct option is both B and C. Question number 7. IEC 62840 standard type is related to A. EV interface, B. Communication, C. Conductive charging, and D. Battery swapping. Okay. D. Yes, it is a correct. For battery swapping, IEC 62840 is a standard which is related to. Question number 8. The terminal of a battery decreases with of while being charged. Okay. The first option is increased charging rate, B. Increasing state of charge, C. Increasing temperature, and D, all of the above. ठीक, ये बता. So here आंसर है कि टर्मिनल ऑफ द बैटरी डिक्रीजेस. टर्मिनल वोल्टेज ऑफ द बैटरी डिक्रीजेस कैसे होता है? चार्जिंग रेट से ज्यादा करेंगे तो टर्मिनल ऑफ वोल्टेज ऑफ द बैटरी विल डिक्रीज. नो, एसओसी इंक्रीज से नहीं. जैसे जैसे टेम्परेचर इंक्रीज करते रहेंगे, होता रहेगा, तो टर्मिनल वोल्टेज ऑफ द बैटरी विल गेट डिक्रीज व्हाइल बीइंग चार्ज्ड. ओके. क्वेश्चन नंबर 9. Which, yes, sir. The ILC converter works on the principle of, क्या होता है ILC? इंटरलिंकिंग कन्वर्टर्स. इनका वर्किंग प्रिंसिपल क्या है? पहला, इक्वलाइजिंग द DC साइड. यस, फिरोज. Yes. If you have any question, you can write in a chat box. Okay. On a DC side, per unit voltage with AC side, per unit frequency. Okay. B, equalizing the DC side per unit voltage with AC side per unit voltage. Okay. C, none of the above. D, both A and B. So tell me the right answer. Actually, uh, the correct answer here will be equalizing DC side per unit voltage with the AC side per unit frequency. Okay. Now, one thing here is that another question which I will like to ask with you. Just a second. We will wrap up with this. Okay. ये आखिरी क्वेश्चन है. फिर इसके बाद हम, okay, which of the following is the IT equipment safety standard? Okay. Question number 10. फर्स्ट है IEC 62196-12-123. बी है GB/T 20234-123. दिस इज चाइना. सी IEC 609-501. डी, नन. ठीक है. तो इसमें बताओ कौन सा जो है स्टैंडर्ड आईटी इक्विपमेंट सेफ्टी को करस्पॉन्ड करता है? Okay, so I will write it here. The this correspond to the which IT equipment safety. This is the correct answer. लेकिन ये किसको correspond करता है? This one. This is correspond to the interface. Okay, plug, socket, vehicle couplers, and this correspond to the connection set of EV. ठीक है? तो ये इसको correspond करता है. I hope you know कि you get a better idea about the topic. And this whole lecture will be shared on the YouTube, so you can, if you have any question, if you missed any part, you can go on there and see revisit the lecture. Okay, because I will upload this lecture on the YouTube, so you can at any point of time, if you don't know, you don't get the point, you can visit that. Okay, so thank you for coming. If you have any question, you can ask. Otherwise, it's all for today. We will meet next week with another topics. Okay. एंड रिगार्डिंग द एग्जाम पैटर्न तो देख सकते हो जाके एनपीटीएल की वेबसाइट पे किस तरह का क्वेश्चंस आएंगे, क्या आएगा. ओके, सो दैट विल बी द थिंग. फिरोज, इफ यू हैव एनी क्वेश्चन, you have raised the hand. After that, I think he left. Okay, no problem. Thank you. Good evening.
Thank you, sir.
Thank you.